Hello, everyone. I can tell that you guys are ready to go already. That's awesome. So happy to see all of your guys' questions and you're ready for chemistry today. So real quick, just want to announce little things that I'm doing and then I'm going to answer as many questions as possible in an hour. So one thing that I've been working towards is getting 10,000 subscribers, as you may or may not know. And if we reach that goal, then what I'm going to be doing is I'm going to be doing a live Q&A to help you guys prepare for your finals, which I know typically you guys have finals in May. If that's different, please let me know when your finals are. That's always really, really helpful to know when your actual final is. So once again, if you guys help me get to 10,000 subscribers, so share my videos, let people know who, can benefit from this resource, can benefit from a chemistry tutor, please let them know. And we're growing each and every day. So hopefully by May, we'll reach that 10,000 subscribers goal and I will do an 8-hour live Q&A, which I know will be so beneficial. Awesome. Molly says end of June. Perfect. That helps me know when to do this. Okay. So that being said, let's just start off with the first question. Let's see what our first question is. We really have a bunch of questions going. And then, one more thing actually that I wanted to say, if you guys have a specific question, which I see a lot of you guys already have put in the chat, which is awesome, I would say I prefer specific questions. The reason for this is because it helps me know what you're confused on or what you need the most help with instead of just a generic or general topic. So if you have a specific question, please put that rather than just like a broad topic. All right, so let's start off with Vincent. He says, I am taking AP chemistry this year. My exam is soon. In your opinion, what are the best chemistry resources to study? I've done practice tests and I am getting 4s, but I want to get a 5. Congrats on getting 4s, by the way. That's awesome. So what I've seen and what I've helped my students achieve was, yes, it is going to be a lot of practicing. You already are on the right track with doing practice tests. The next thing that I want you to do is I always tell my students to make like a cheat sheet or like a guide, and you're going to write out all of the main topics that you learned this year. So like, let's say with gas laws or whatnot, write down all of the laws that you have to know, right? All of the formulas that you have to know. Then write down pretty much the main patterns or the same questions that you keep seeing. And then once you know what topic, like think of it as you're looking at every single section and you're seeing the important topics that they always throw. So that's something that personally I would always do for exams in general, is especially a final exam, is I look back at all of the tests and I see what are the common questions that they always throw. And then I know what to focus on, what to remember and whatnot. So make sure to do like a huge list of just, maybe in the beginning, nomenclature or stoichiometry, and just seeing what are the main like important things to know from that section. And then that's going to help you out. And I really believe that's going to get you to that 5. And then once you practice your tests, again, keep practicing those tests. You'll have a guide and know what you need help with. Hope that makes more sense. And I hope that helps you out. I'm going to move on to Eleanor's question. Hi, Melissa. Could you explain about the Lewis structure of polyatomic ions, for example? Okay, so let's start off with this example. And with Lewis structures, we always want to count how many valence electrons we have. Okay, so that's what I'm going to start off with. I'm going to start off with carbon. We know carbon's valence electrons are 4. Oxygen has 6, but there are 3 oxygens within this polyatomic ion. So I'll multiply this by 3. So then we'll get 18. Now I'm going to add these two together. And there's one more thing to do here. Because this has a charge, so that 2- charge, whenever it's a negative charge, you're going to add on to the electron count that you have. If it's positive, it's a plus charge, you would subtract that amount. So I'm going to add 2, and then let's see what we get. So this would have been 24 valence electrons in total. I always like to start with that just because that helps me draw this out. All right, so your central atom is going to be carbon, because it's always going to be carbon, by the way, if carbon is within that compound. So I'm going to surround this with 3 different oxygen. And the first thing I'll do is just count up all of the electrons. What I like to do is I like to put the lone pairs on the outer atoms first before I start adding on to the the central atom. And then, so let's do that. So let's do 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And let's see if we have enough. So I counted 18 lone pairs so far. And then so 18, 19, 20, 21, 22, 23, 24. And so far you would think that that is happy and complete, though it does have 24 electrons. This is not content. This is not fulfilling that octet rule. Remember, the octet rule means that our central atom wants to have 8 valence electrons, and carbon absolutely follows that octet rule. So what's going to happen is we're going to move some electrons. We're going to form a double bond, and it doesn't matter which oxygen you choose to put that double bond. And what I'm going to do is I'm going to form a double bond between this oxygen. When I do that, I'm reducing the amount of electrons because essentially I'm moving them. So to form that double bond. And then this is what our actual structure would be. One last thing, whenever it's charged, you always want to place that Lewis structure in brackets and put the charge on top. So that would be our proper structure in this case. And then one more, you stated NO3 with a negative charge, same concept here. So what I'll do, count up the valence electrons to double check that we will draw this correctly. So nitrogen has 5. Oxygen again has 6. Multiply that by 3 gives us 18. Once again, we have that negative. So this negative means we're going to add one more electron. And I'll add everything up. So 5 plus 18. So let's see, we'll have really 6 plus 18. So 24 again. And then in this case, nitrogen will be our central atom. I'll surround that by 3 oxygens, and it's basically going to be the exact same structure as we saw before. This was, here we go. This was our overall, this had 24 electrons. Now, what I want to do next is let's see what else we'd have. And let me double check that I did everything else. Yeah. We're not done just yet because nitrogen only has 3 electrons. So, and how I know that is because this has 1, 2, and 3. So that's not complete. That's not happy. So what I'll do is once again, I'll move a lone pair and I'll form that double bond. So this would have formed a double bond. It removes one of our lone pairs. And let's keep going, and I'll double check that this is complete. Well, nitrogen here is still not. And instead of having to show, let me show one little thing. Because formal charges is something that's helpful. Give me one sec. All right, so we're not done just yet. And how I know this is because nitrogen must have 5 valence electrons, as we stated in the very beginning. This does not. This only has 1, 2, 3, and 4. So I need one more. So I'll transfer, or not transfer, I'll move lone pairs again. And now this is happy. So this would be 2 double bonds on our oxygen. And then how I knew that, once again, was just the fact that in the beginning, nitrogen, we said, had to have 5. So now this has 5 valence electrons, 1, 2, 3, 4, and 5. So, okay, right then and there, that's happy. And then lastly, just put this in a bracket with the charge on top, and that would be our proper Lewis structure for those. Hope that makes some more sense. And let's move on to Tuyen. You have 2 questions. I'm going to start off with the first one, answering the first one. So what is the wavelength in meters of an X-ray with the frequency of that amount? Calculate the energy of 1 mole of yellow light, and our wavelength is given. So let me go ahead and write all this down. Okay. So we're solving for wavelength in meters. So we want our wavelength in meters, and we're given our frequency is 2.5 times 10 to the 18th hertz. And what else? Calculate the energy of, oh, there's 2 questions within that. Got it. So I'll start off with the first question. So with this one, it's the main thing to look at is what is your formula, right? That's going to be the main process of this. And let me grab my formulas. But you're always going to start off with just identifying what formula you have. There are several. However, the one that I'm going to use specifically for this one has to contain frequency and wavelength. And the formula for that would have been our frequency is equal to the speed of light, which is a constant, divided by our wavelength. Now, I'm going to write this or rearrange this formula so it's solving for our wavelength. And what I'll do is I'll just multiply both sides by our wavelength to cancel out that denominator. That cancels out. Now we have our wavelength times our frequency is equal to c, or the speed of light. Next, I want the wavelength to be by itself. So I'll divide our frequency over. And then now this finally gives me the proper formula where our wavelength is equal to our speed of light divided by our frequency. Now, we can't just plug in just yet. And the reason for this is because we always want to check our units when we're looking at these types of like wavelength and frequency. That's always the trick, by the way, is the units, though it can seem a little bit easy once you get the formula to plug in, that's where they get you. So be careful of that. So with our speed of light, that is 3.0 times 10 to the 8th meters per second. Now, our frequency is in hertz. So this has to be changed to seconds. Something to note is that 1 hertz is equal to 1 second to the negative first. So all I have to really do is just change that automatically. There's no math really involved. So this is 2.5 times 10 to the 18th seconds to the negative first. Now I can plug in. And though I know that that one, we didn't have to do any math, that unit you would be marked down if you didn't show that. Okay, so beware of that. So on top, I'm just going to plug in our speed of light and then divide it by the frequency, and then that would be our final answer. Because as you can tell, what would happen is these seconds and seconds would cancel and we would be left with meters. So now let's just divide and see what we get, and then I'll answer the last chunk of your question and move on. So 3.0 to the 8th, and I'm going to divide that by 2.5 18th. All right, what do we get? So our frequency is then 1.2 times 10 to the negative 10th, and then that would be meters. So that's the main thing for that first one. Now, if we're calculating energy, we're going to figure out, or we're going to see that we have a different formula. So our energy formula, we have two different types. We have one that shows our Planck's constant times the frequency, or energy is equal to Planck's constant times the speed of light divided by our wavelength. So let's look at first just what in the world we have. What we're given is just the wavelength. So since we are just given the wavelength, I'm going to use this formula. The reason is because we don't have frequency to use this one, so that's why that one's out. So now let's see what else we have. Our wavelength is 612 nanometers. Okay, so before we do anything else, what you want to do is convert your nanometers to meters, all right? Beware of that. Once again, people tend to just plug in and that's how you get it wrong. So let's convert this to meters, where 1 nanometer on the bottom and it's 10 to the negative 9th meters. After we multiply straight across, this would have given us 6.12 times 10 to the negative 7th meters. Okay. Now we can just plug in because h, or Planck's constant, is just a constant that is given to you. It's 6.626 times 10 to the negative 34th joules divided by, actually, times seconds. And then we said the speed of light was 3.0 times 10 to the 8th meters per second. So now that everything is in the proper unit, and how I knew that, we always want our wavelength to be in meters whenever we're plugging in. And then before you saw, we want, seconds, so those can cancel. And then eventually we'll get joules, which is the unit for energy. Now I'm going to plug everything into our formula. And really, we're just multiplying the top. So this is Planck's constant. All right. And let's multiply that by our speed of light. 3.0 times 10 to the 8th meters per second divided by our wavelength that we just changed to meters. And once again, what would happen is our seconds and seconds would cancel, meters and meters cancel, and we're left with joules. And we'll multiply straight across and then divide by that wavelength. So 6.626 to the negative 34th times 3.0 10 to the 8th divided by our wavelength. Let's see what we get. So our energy is then equal to 3.24 times 10 to the negative 19th joules, and that would be our final answer. So main thing, always check what formula are you using and double check your units. All right, let's move on to the next question. Samantha. So Samantha states, hi, Melissa. I had a question on the difference between ideal and real gases. I was also wondering if you could go over problems using combined gas law. I'll start off with ideal and real gases. So with our ideal versus real gases, this goes back to our kinetic molecular theory. Now, what that essentially is talking about is how a gas behaves. So if we were to look at, let's say, something that behaves ideally, there are certain conditions when it comes to something behaving ideally. And that's actually why we automatically start with our ideal gas law, right? Where we have a gas constant R, and then we're always measuring pressure, volume, moles, and temperature, and those are all kind of related. Now, the main difference with this, and I'll do like a little chart here, I'll start off with just something that's an ideal gas. If something is ideal, it's going to have small particles, okay? So, and I want you to think of gas particles are very small. That's always what I'm reviewing, by the way, guys. What I'm reviewing is the kinetic molecular theory. So these are just the main points or postulates to go along with the theory. So the first one is just that gas particles are small. Are small. Okay. Now, if I were to compare that to our real gases, that's actually the same. And I'll show you where they differ in a second, but so far that's also the same. Now for our next portion, gases are mostly empty space. Yep, that is the same for this as well, where gases are empty space, mostly. Okay, and then next, we want to look at how gas particles are moving. They're in a constant, random, straight motion. That's how they move. So I'll state that they are constant, random, straight line motion. Okay, and that's the same thing as well for our real gases. And now we're going to get to our change and see the difference. So with an ideal gas law, or an ideal gas, I'm sorry, we look at the fact that if we have two different gas particles, they're not going to be attracted to each other. They're actually going to, they don't really attract or repel each other per se. They're always just moving in constant motion. Sometimes they are elastic, which we'll get to, meaning that they will bounce off of each other. Think of it, I always kind of like to think of it like a bouncy ball. If I were to just fling it at a wall, it's going to keep going. It's going to keep hitting different things, hitting different motions. It's random. You can't really predict always where it's going to go. And it is in that straight motion. So that's how I kind of constantly think of it. But now for 4, what we're looking at is there is no attractive or repulsion, and then forces overall. Okay. However, for our real gases, there is a very, very small attractive and repulsive forces. So I'm going to say very small. Okay, and I'm looking at just attractive or repulsive forces. That's one of the major differences. Next, and I meant to put 4 here. Next, for our ideal, we don't really care about volume. They have no volume. So particles, gas particles, they don't take up space. We said they're made up of empty space. So right then and there, no volume. However, for our real gases, particles take up a very, very small volume. So very small volume. Okay, and then next, lastly, we're going to go back to those collisions that are elastic, meaning they pretty much like bounce off of each other. There is no loss of kinetic energy. What kinetic energy is, it's the energy of motion. So currently right now I have potential energy, meaning I have stored energy. I'm sitting down. However, if I were to stand up and start running, then I would have kinetic energy because I'm moving. All right, so here the last one would have been collisions are elastic. Okay, so let's move this over. So no loss of, I'm going to say KE, meaning kinetic energy. And lastly, for this one, collisions are inelastic. And what that means is we will have a loss of energy whenever they collide. So loss of energy. Okay, so those are the main differences. That's the main thing to look at. That was one of your questions. I am going to move on to another. And if we have more time, of course, I'll go over the combined gas law. However, I do have a previous video on, what was it? It was a previous tutoring session, live tutoring session where I talked about the combined gas law. Make sure to check that out. Another thing, guys, is I just released another really, really detailed notes. Think of it like a how-to guide for all of your gas laws. So if you're confused on gas laws, if you want more practice, need more help to prepare for your exam, I highly, highly recommend checking it out. It is in the link is in the description box of this this video and pretty much all my other videos. So make sure to check that out. It's gas laws, everything like partial pressures, Dalton's law, which is partial pressures, combined gas law, ideal gas law, everything that you need, gas stoichiometry to cover these topics I have put in there. So extremely detailed examples. Make sure to check that out. And let's look at the next question. So it's Stephanie asks or says, I am still confused with nomenclature. I watched your videos and they are super helpful, but on my own, I cannot get the right formula or name. Okay. So Stephanie, I'm glad that the video felt helpful. Now, what might be the case here is maybe how we're approaching the problem. So what I want you to always do with approaching these nomenclature problems is just looking at what type of compound it is initially. And that's going to help tell you, okay, am I going to balance the charges or am I going to put some sort of prefix in front if I see a subscript? So let's say if we had something like this, and let me make this up real quick. So let's say if I had, and that, we'll say 2. I'll give you a couple and then I'll show you how I can just tell. Okay, and one more, and I'll show you what I always like to do initially. So let's do, sure. Okay, something like this. So what I like to do initially is just to figure out what in the world, what type of compound is this initially, all right? So if it's ionic, that means we have to balance out our charges. And remember, an ionic compound is a metal and a non-metal, or really a metal and some sort of polyatomic ion, okay? So with iron, that is a metal. So that always has a positive charge, we know that. And then hydroxide, or OH, that is a polyatomic ion, meaning it's a negative charge. These opposite charges tell us that it is an ionic compound. Now we have to figure out what charge would our iron have. So a lot of times for our transition metals, we do have to state the Roman numeral, or that just tells us the charge. So I'm going to start off with the name of the metal, so iron. Now we have to figure out the charge. So iron, we don't know what that initially was because that can change. It could either be a +2 or a +3 charge. Now, hydroxide, this comes back to our polyatomic ions and having those memorized, unfortunately. So our OH has a -1 charge. And because there's a -1 there, now going back to what we were given, this 2 is your hint to go backwards and see that iron must have had a 2 charge. So I'll put 2 for our Roman numeral. And then next, the last thing here is just to write what our OH was, which is hydroxide. So that would be the proper name. And then let's do our next one and first identify what type of compound this is. Well, we have P, which is phosphorus, and N, which is nitrogen. Both of those have negative charges, or we could even think of it as they both are nonmetals. Whenever we have nonmetals coming together, then we know that that is covalent, so there will be no balancing of charges. The subscript will tell us how many of each there are, meaning we're going to put a prefix instead. So what I'll do is just looking at this subscript of 2, remembering our prefixes 2 means, or di means 2, so then I'll put di, then I'll put the actual name of the metal, so P is phosphorus. And there we go, phosphorus. Okay. Spelling, right? Spelling these elements are sometimes like, what? And then nitrogen, Now, the last portion here for nitrogen, that's always going to end in "ide." So the last one, right, the nonmetal always ends in "ide." However, here we also have a 5. So I'm going to say pent nitride. So that 5 just tells us pent nitride. Another thing I've seen, penta nitride, oftentimes they remove the A and just put the actual name of the nonmetal, so ending in "ide." So that's something to look out for, but typically I see like pent nitride. So that would have been for our covalent, so no balancing of charges whatsoever. And then lastly, this is a little bit of a different one where we have oxygen at the end and we also have mercury. So we have Hg, which we have to know that's mercury. Now, mercury is one of those ones that it is a transitional metal, and it also has a different types of valence or electrons in general. So different charges, I'm sorry. So what I'm going to look at is oxygen's charge. Oxygen has a 2- charge typically. So for there to be no subscript for mercury, that means it had to have been balanced already. Our charges had to be balanced. So this must be a 2+ charge to cancel that out and require no subscript. So now I'll write the name of the metal again, so mercury. And then I'll also put 2, since that was the charge. And then our nonmetal always ends in "ide, so instead of oxygen, it would be oxide. So I really, really recommend doing that trick, just looking at what do I have initially and then going from those rules. That's how the video is designed to help you guys out, is doing that strategy. And really with naming, to be honest, it's looking at it so many times and getting familiar with all the names. And so practicing as much as possible is my recommendation for really anything. So, all right, I hope that helps. And I'm going to move on to Molly's question. Okay. Let's see. Okay. So Molly asked, when 2.50 grams, and I'm going to start jotting this down, grams of ethyl alcohol is vaporized, the vapor is found to have a volume of 1.68 liters at 100 degrees Celsius. And then we're also given our pressure. So this was our temperature. And our pressure is 100 kilopascals. Okay, define or determine this amount of gas. Can you go over what the ideal gas law is? Sure. So with this question, and even before getting into this question, let's just look at our ideal gas law, which is this formula. Now, with the ideal gas law, our units have to be specifically these next ones. So pressure always has to be in atmospheres. Okay. Volume has to be in liters. N is moles. And then R is just a gas constant. So that is typically given to you, or depending on your teacher, the typical one that you'll see is 0.0821, or you might have seen 0.08206. Either of them work, by the way. I typically use this one. And then now our units for this would have been liters, atmospheres divided by moles, Kelvin. And that's actually the reason why we want everything to be in these proper units, because our gas constant tells us what unit it wants. And then by putting everything in the correct units, everything would cancel and give you what you're looking for. And of course, for all gas laws, our temperature has to be in Kelvin. So that's what I'm always going to start off with. Whenever I see it's an ideal gas law formula that I have to use, I always change the units. So let's do that. So let's start off with, we know our volume is totally fine. So our volume is completely fine with that. However, okay, that's fine. So what she's using there, Molly, you said that she's using a totally different gas constant. That's fine. We have several depending on what pressure you're using. I can show you how to use that one. The reason why I always use one is because so you don't have to memorize them all. So you don't have to remember how to use every single different one. How I personally like to teach is I like to give you one way that works every single time instead of having you guys have to remember all these different ways. But I can absolutely teach you how to use this specific gas constant. So 8.314 kilopascals divided by moles Kelvin. Oh, there should be liters on top. Okay. So I'll show you how to use that one. No problem. So instead, I just have to actually change the temperature. And what I'm going to do is I'm going to convert this to Kelvin by adding 273. So when I do that, that changes it to Kelvin, and we'll get 373 Kelvin. And then I'll leave kilopascals since we are using the specific gas constant. Okay. All right. So let's plug everything in. And then next, let's look at this. So pressure, volume equals, okay. I'm going to plug absolutely everything in. And I know we have pressure was given as 100 kilopascals. And then our volume was given as 1.68 liters. And then now our moles is something that we need. Actually, is that what we're looking for, right? The only other thing that I want to look at, hold on, determine this amount of gas. The amount of gas, or were you stating, hold on, because I believe this question is actually asking the molar mass. So it's asking, I'll get to it, but I'm still going to figure out the amount of moles. But I'm just curious why they're giving us 2.5 grams initially. We'll go over it. 8.314 kilopascals. Just plugging everything in, guys, and then we'll solve for N, which is moles. Okay, and then this was temperature 373, I believe I said, yeah. Okay, so I'll multiply these two together and these two together, and then we'll keep going from there. So this really would have been 168 kilopascals times liters is equal to 373 times 8.314. So this amount roughly. And then this would have been our Kelvin and our Kelvin cancel. So now I have kilopascals times liters divided by moles. And then this is still times. I'm going to put N in front. Okay. Amount in moles. Okay. Yeah. I figured. I was just curious why they were giving you anything else. But yeah. Because sometimes they do ask for the molar mass or the identify what type of gas it is. So what I'm going to do is I'm going to divide everything over for right now just to solve for our moles. So dividing this entirely over, I wanted to show you how your units would then cancel. So we'll see that kilopascals and liters would cancel. These two cancel and we're left with moles. I'm just going to divide and then I'm done for this first one. So 168 divided by this value, we'll get roughly 0.05. I'm going to check my sig fig count, and we had technically just 1 because it's 100. So I'll leave it here, and then this would have been moles. So that would have been our final answer. Okay, I hope that makes some more sense. If you need more help with the ideal gas law, I do have a video on it. So make sure to check that out. And as mentioned, guys, if you guys want more help with gas laws, make sure to check out the detailed notes that I created. Extremely helpful, especially for your exam, because I have placed all these different types of exam questions that teachers have typically put on their exam, the wording and everything, just understanding that. So that link is in the description box of this video. All right, so let's move on to the next question. Mohammed says, I need help with acids and bases. Mohammed, what exactly with acids and bases? Please let me know. Maybe a specific question. Are you having trouble with conjugate pairs or what? So guys, whenever you guys are asking a question, I ask that you let me know specifically what you need help with instead of just a general topic, because I can talk about that for hours, but we don't have that time. Okay, so Mohammed, please let me know if you have a specific question. I am going to move on to the next question, but if I'll go back to yours if you play something, okay? So next I have Batul saying review trends in periodic table. Okay, so for our different trends, we'll go over, like Mohammed said, I wrote it down. Let me see where you wrote it down. Oh, there it is. Perfect. Thank you so much. I'm going to go back to Mohammed's question, then Batul, I'll answer yours as well. And we have time to answer both, don't worry. So Mohammed says, which type of reaction occurs when H hydrogen that's aqueous reacts with OH. Okay, so reacts with OH and it's also aqueous. And reacts with that. Oh, I see. It's a multiple choice question. Okay. It's asking combustion, fermentation, decomposition, or neutralization. Okay. So really what's going to form is just water. This is a neutralization reaction. And how I knew that, by the way, is because anything that typically starts off with an H is an acid. Anything that has OH or ends in OH is a base. Okay. So water is going to be formed here, and we can tell that since we have H and OH. Sure, I'll explain the terms as well. So H and OH, that forms H2O, which would then be a liquid. Now, this is specifically what everything is going to form. This would have been like I said, a neutralization reaction. What a neutralization reaction is, it's going to have, we have an acid where, let me explain what an acid is and how we know it's an acid. So an acid will donate a proton, and all that is, a proton, really they're talking about something with a positive charge, or specifically an H+. And then while a base will accept that proton, or it accepts a H+. So an acid will lose or give away its H+, while a base will accept it to form, like in this case, this is a little bit different since it's a specific reaction, but this is the main kind of concept behind an acid and a base. And I mentioned that an acid typically starts with an H, however, a base would end with a OH. Okay, so this is a minus charge, this is a positive charge. That's something to kind of look at. So that's the concept of neutralization reactions. If we were to keep seeing a neutralization reaction, this isn't one, this is a different case just because water is very specific. It could act as an acid or a base. It's called amphoteric, just meaning it could act as an acid or a base. Now, if I'm really looking at a neutralization reaction, that would have been something like HCl plus NaOH, and that would give us NaCl plus water. And how I automatically knew that, by the way, whenever we have an acid, so acid starts with H, if I add that to a base, we said a base ends in OH, that will form a type of salt, which, by the way, a salt is really just an ionic compound, meaning it consists of a metal and a nonmetal, and then it's always going to also produce water. So that is the concept of a neutralization reaction. I hope that makes more sense with that. I'm going to go back to Batul's question. Okay. And you were asking for the trends for your periodic table. All right, let me pull up all my trends and just go over what the typical trends are. I believe I have that at the end here. There we go. Okay, I'll start off with electronegativity. So when we're looking at electronegativity, let's first identify what in the world electronegativity is. So electronegativity is essentially talking about how an element is going to attract an electron, okay? So think of it as, like, let's say if something is very electronegative, that means it has a better chance of attracting another electron. If something is not so electronegative or not electronegative whatsoever, then it's not going to attract that electron well, okay? So that's the concept behind this. How this works is we're going to increase as we move from left to right, and as we increase, as we go really from down to up our column. So this is increasing for our electronegativity. How I personally like to think of it is whatever is closest to fluorine is electronegative. Now, fluorine is the most electronegative atom. That's just something known, okay? So definitely remember that. And then one more little thing, there is an exception to this rule where our noble gases, so anything like helium, remember that last column on our periodic table, noble gases are not electronegative, okay? So make sure to note that. The reason for that it goes back to Lewis structures and valence electrons, where the fact that noble gases are already complete. So they have 8 valence electrons. They're happy. They're content. They kind of obey that octet rule, right? So that's why they're stable and they don't need an extra electron. So that's the concept behind electronegativity. Now I'm going to go to another one where let's look at, let's say, ionization energy. And I'll go over the trends here quickly, and then I'll move on to another one. So ionization energy is a little bit different. It's the same trend, by the way. It's the same exact trend where we're increasing the same way. Okay. Now, the concept here of what ionization energy is, it is the energy required to remove an electron. Okay. Remove an electron. That's essentially the concept with it. So energy that we need to actually take away an electron. So the main thing, again, the highest one once more is our fluorine. That's another thing that we're looking at. And that's going to be our general trend again with ionization energy. And there's a couple more trends and then I think we'll get it from there. Let me erase this one. This one's really, really similar. So let's say we have electron affinity, which once again, it's the same like trend for our periodic table. So electron affinity is the energy required to add an electron. So this time we're adding. So electron affinity, we're going to add, we're trying to see how much energy is needed to add an electron. And then once again, it's the same exact trend. And then now we'll start to change the trend. Okay, finally. And I'm going to go on to, let's do atomic radii. For atomic radii, essentially what we're looking at, and this is actually the trend, this corner is going to be the strongest or the highest, essentially. So what I want you to think of is for atomic radii, what we're looking at is, let's say if we were to have, it's kind of like the size of our radius of that atom. Okay, think of it that way, where what I'm doing is that I'm increasing. So here we're going to start off smaller and then gets a little bit bigger. And it keeps increasing, keeps increasing, keeps increasing. So that's the concept there, is just kind of the size overall. And then let's see. And that's actually the main one. I have one more to do. This is increasing, by the way. One more to do. Okay, and then next, metallic character is the last one. This one is essentially talking about how likely it behaves as a metal. So like what properties or characteristics does it have that it actually goes to be a metal? So think of a metal as being, on one, we know it's positively charged. 2, we know it's malleable. We know we can, it can be a good conductor of electricity. That's one main one to note. Does it have similar, like depending on a boiling point, melting points and whatnot. But essentially what we're looking at is it's going to increase in this direction as we kind of go diagonally across the periodic table. So that's the main concept. And I had one more thing. Mohammed, I guess I didn't get what else you wanted. That was, you wanted the actual terms. I see. Okay, so I went over neutralization. I went over what that was. Decomposition was basically the splitting of a compound. So like, let's say if I were to go backwards now, and if I start off with water, you have a compound and you're going to break it apart into its elements that it was needed to form it initially. So think of it as like the elements that we needed to form this was hydrogen, and that's hydrogen gas, plus oxygen gas, and this is unbalanced, by the way. But this is decomposition, where you have a compound, you're breaking it apart into its components or its elements that were needed. For combustion, and I'll go to fermentation. I want to give you an actual example for fermentation. But for combustion, there is a specific reaction for this. And here, because fermentation is a bit more complicated of a reaction. So we'll see what you want with that. But here, let me go over combustion first. So with combustion, what we're always going to see is we're going to start off with some sort of hydrocarbon, what that means, it's a carbon and a hydrogen. Let's say CH4 is one. This is going to constantly be changing. What never changes is it's always going to be attached to O2. So we're always going to be combining that with oxygen gas. It's going to then have heat. So combustion, think of it, something's kind of like exploding in a way, but we have heat, and then that's going to form CO2 or carbon dioxide and water. This is always the case. So this portion is never changing for a combustion reaction. And lastly, for our fermentation, fermentation is going to give you, and we'll see what specifically your professor would want for that, but you typically start off with the sugar. So like, let's say glucose, and that is going to give us, by the way, you add like yeast or whatnot, and what you're going to end up getting is some sort of alcohol. So this is known as ethanol, and then carbon dioxide. So that's essentially what you're going to have. You're going to have some type of sugar. In this case, this is glucose. And then you'll have some sort of alcohol. And how I know this is an alcohol, this is kind of more organic chemistry, but it does have an OH group. However, this is different from a base. Okay. So, and then it does have carbon dioxide. So that's the main process of each one. Hope that makes more sense. And let's move on to another question. Let me refresh this. Okay. Okay. Martin asks, can you explain equilibrium and the equation? Sure. And I'm going to go over, I guess, a general thing. If you have a specific question, definitely let me know within. But equilibrium essentially is talking about when our reactants and our products are equally balanced. So whenever we're looking at, and I'm not talking about balancing equations, by the way, I'm looking at the reaction. So when we're essentially looking at equilibrium, I want you to think the entire reaction is balanced. Okay. So let's say if I had, I'm going to just make something up, but do one. Let's say if I had HCl, sure, plus water, and this is at equilibrium, and this would give me, okay. Sorry, dinging in my mind. Okay, and then this would give us Cl minus. So something like this. Let's say that this is at equilibrium. Essentially, what I'm talking about is the rate of our forward reaction. And forward reaction, I mean going in this way, going from reactant to product, is then equal to the rate of our reverse reaction. So that means if I were to go backwards, going from product to reactant. So that is essentially what equilibrium is when our forward reaction is equal to our reverse reaction. And then the equation for that, I believe you're asking for our constant, our equilibrium constant, which is known as Kc. So for this specifically, it would have been the concentration of our products divided by the concentration of our reactants. So let's say if I were to look at, I kind of want to give you a different one because that wasn't the best. I mean, the example was fine for equilibrium, but not for our equilibrium constant. Or actually, you know what? Yeah, why not? Why not? And I say that because I'm just going to put the states, and then I'll tell you what states to avoid that we don't put in the equilibrium constant. So this is aqueous, water would be liquid, this would be aqueous and aqueous. So what I'm going to do, and this is completely balanced, what I'm going to do is just the fact that I'm going to look at the products first and put the concentration. So how I'm going to write this is that Kc is equal to the concentration of our, this is known as hydronium, and hydronium just means acid. Okay, really it's just an acid. So that's the concentration of that. And then I'm also going to put our chlorine ion. So on top, that's our concentration of our products on top. And then now I'm going to only put the concentration of HCl. And the reason for this is because whenever we're looking at Kc, or really the equilibrium constant, we only look at putting anything that's aqueous or a gas. So we never want to include a solid or a liquid. That's just something to note. So that's why I'm only going to put HCl on the bottom. Now, let's say if, and I know this doesn't work for this specific one, but let's say that there was a 2 coefficient in front of HCl, okay? If there were a 2, then what I have to do is I have to put a exponent of 2, okay? So that tells me that this exponent really refers to the coefficient that was in the balanced equation. So definitely be aware of that. That's how you look at our equilibrium and equation. Hope that makes more sense. Let's move on to another one. Can you please go over acids and conjugate bases? How to identify them? Perfect. This goes perfectly. I just did one. So let me go over that. All right, Norma. So here we go. Let's go back to this question. So I'll go back to HCl and I'm going to add water. And let's say I'm actually trying to figure out which one is an acid, which one is a base, what's the conjugate base, acid pairs and everything, okay? So this goes back to the definition of what an acid is. This specifically is going over the definition of Bronsted-Lowry. And essentially what that's saying, again, is just the fact that an acid will donate, right? Donates a proton or H+, and then a base will gain, or really gain or accept an H+. Okay, so it is very important to know what is an acid and what is a base. How I mentioned it before, where an acid we know normally starts with an H. So here HCl most likely is our acid. Well, it is. And then H2O can act as either or. It could act as either an acid or a base. So you always want to be aware of that one specifically. Since I just identified that HCl is our acid, then I know it's going to give up or donate an H. So literally, this H is going to be donated to our base. So far this is our acid, this is our base. And then now I can figure out what our conjugate pairs are. So this is going to continue, and then this is going to be, now with our acid, what's going to happen is this H is going to go away, and then we'll form Cl- because it's by itself now. And then by the way, the reason why it's a negative charge, we lost a proton, which is positively charged. Remember, we lost an H. And since that has a positive charge and chlorine now is by itself, we do want to state its ion or its charge. And then now plus, since we're donating an H and our base accepts that hydrogen, then this gained a hydrogen. So now it's H3O+. The reason why it's a positive charge is because it gained an H, which is positively charged. And then now let's identify what's our conjugate base, conjugate acid. So I identified what the acid was. Now let's figure out what our conjugate base is. So those are always going to go hand in hand, meaning this Cl, it can't just magically change to something else. So our pairs still have to look similar, okay? So that's how I knew that this must have been my conjugate base. Because one, it looks similar to the acid, right? It has that Cl and Cl. And another thing is just the fact that your acid starts off with an H and then it loses it. So that's why I can tell that my conjugate base would be Cl-. And then now vice versa for my base, then our base starts off with a little bit less of hydrogen, and then it ends with an extra hydrogen, or it gains a hydrogen. So that's how I knew that these two have to be pairs. So this is the conjugate acid. Okay, so that is the major concept with this. It's just seeing how we're kind of moving everything around, understanding what's your acid, what's your base, and how it's going to behave. And like I mentioned, they have to look similar to each other. So this Cl can't just disappear. They have to, it's always the ending portion, by the way, that looks similar. And then our base, you can just tell since it gained a hydrogen, and once again, it still looks similar, has that oxygen, and those two are conjugate pairs. Okay, hope that makes some more sense. I'm going to move on let's look Maria's question. So Maria says, find our change in enthalpy for this reaction. Use the following reactions with known H's. I don't know if it cut off. This looks like a Hess's law problem. And I don't know if it cut off. I'll see what I can do. Use the following. Yeah, no, it is a Hess's law question. We're looking through and seeing if Maria, if you have the question again, please put it back in the chat. If not, I think I might just move on because we have barely any time left. No, the fall, I think it's cut off. I don't know if you're still there. Yeah, I don't see it. I'm going to move on to another question. Sorry about that. Let's look at why are, Mather says, why are some salts soluble and others are not? Okay. So when we're talking about solubility, essentially we're looking at what is it going to be dissolved in? And typically it's water. Okay, so water, this goes back to polarity, by the way. So when we're looking at polarity, water is definitely polar. And the reason for this is it's because oxygen is very electronegative, plus we have lone pairs on our central atom. So this makes it very, very polar, just going back to like Lewis structures. So what I'm going to do is whenever we're looking at something being soluble, there's a kind of like process that you kind of say that like dissolves like. What that means is that if something is polar, it will dissolve in something that is polar. Okay, so that's the general concept here. And let's say if they were opposite from each other, let's say if we started off with something that was non-polar, that's why it won't dissolve. It's not going to dissolve in something that is polar. So that's the main concept to look at, like dissolves like. If we were to look at an example of this for solubility, this also depends on a lot actually, but that is the main concept. I hope that's making some more sense. But like, let's say NaCl, this will dissolve in water. And the fact of this, it's just the fact that this is a good salt. We would also look at the fact of whether it's, I don't think you guys have gone over whether it's acidic or basic, but I hope that's making some more sense, Mather. If I would have to look at a specific question because there are different factors. But what you would look at, by the way, if I'm assuming this is what you're doing, you're looking at what type of salt is it? Is it neutral? Is it acidic? Is it basic? And looking at, you know, that specifically. How you would see that, by the way, is like, let's say if we had NaCl, this is actually a neutral salt. How I knew that was Na would tell us it would resemble a strong base. So this is Na, it's part of an ion of NaOH, which is a strong base. And then Cl comes from HCl, which is a strong acid. And then since I know both of them are strong, then this would give me a neutral salt. So it does depend what you're placing it in. Like I said, it's typically water. So definitely check, you know, is it polar initially? Is it non-polar? And how you could also check with that, by the way, is like, let's say if you had, I'm just kind of writing a big old thing, but let's say if you had something like this, okay, this isn't going to be the best salt to dissolve because it's so large. Okay, the fact that this is so bulky, it's not going to be able to completely dissociate or break apart in water as well. Okay, that's another thing to look at. But Laura says, hi Melissa, I was wondering how to get better at acid and bases writing an equation. I am currently taking chemistry honors. So the main thing to look at that is going back to just pretty much practicing. And what you're going to do, like, I'll give you another example. Like, let's say if we had something like this, okay? If I had something like this, essentially what we would look at is still looking at what your acid and your base is. And remember, you probably have a list that you were given of different strong acids and weak acids, strong bases, weak bases, and so on. Okay, but as I mentioned, with acids, they typically always start with an H, and then bases typically end with an OH. Our weak bases are a little bit of an exception to that rule, where NH3 is a weak base. That's a common one. But your strong bases are always combined with groups 1 and 2 and OH. So that's my little trick for you there. Now, the main thing to look at, and how I always like to look at it, is just our acid has to give up that hydrogen, right? So automatically, we don't need a hydrogen. Bromine is by itself. And then what would happen next, and for this specific reaction, I'm actually just going to show OH, but for this specific reaction, what would then form is just water, because Then H is being donated with OH or combining with OH, and then we added an H. So that's the process that I want you to look at is, all right, acids are always going to give up a hydrogen, and so they're going to lose it in their products, making it a conjugate base, right? This pair here. And then for our base, it's always going to gain a hydrogen in the products. So that's the repetition that I want you to notice for that, okay? So, and keep practicing that, just knowing the definition, literally, you know, giving up a hydrogen for acid and gaining a base, gaining a hydrogen for your base. All right, guys, that is my time for today. If you guys didn't get your questions answered, by the way, I do this every single Sunday, and make sure to get here. You guys already came here early. A lot of you guys came here early, which is smart. To make sure that your question got answered. But yes, I do recommend coming here early or being on exactly on time to guarantee that I answer your question. And yeah, and as mentioned, if we hit 10,000 subscribers this time around, I will be doing an 8-hour live Q&A. So that's going to be really beneficial for your guys' finals that are coming up, most likely in May or June, depending on, you know, where you're at in the world. So help me get there, guys. Please share my videos, you know, share my channel with people that can benefit from a chemistry tutor and chemistry tutorials overall. So thank you once again for being here. And I will see you guys again next Sunday. Have an awesome day. See you guys.